a while, so we need to catch him up. So I think we start with a joke. But what we've decided is that instead of just rating the joke thumbs up or thumbs down, or actually you can go sideways, we're also rating it on right. It's a scale. It's more granular than that. You can also rate it for delivery. So content and delivery. Let's get you the microphone. The book, not homemade.
No, this is not homemade.
All right, here we go.
So you can't judge me as much.
No, we can, and we will.
All right, this was a mistake.
All right.
What should you do with a dead chemist?
Oh, I know.
You know?
It's stupid. Go ahead.
You bury him.
Realizing that I'm now exposing myself to the possibility that this is infected. Oh, wait. Okay, right. We got to vote. Okay, so wait. Is right hand content? Left hand should be content. Right hand delivery.
Wait.
0 on delivery?
So I'm in this zone. Yeah. This is a tough audience. You should try teaching these guys. You think it's hard to entertain? Well, actually, teaching and entertainment are the same thing. So, all right. That's right. No, because that is definitely not funny. It is not. Now I'm not amused and my feelings are hurt. I know. All right, guys, so let's gather together as we wrap up chapter 14. Kaylee, I think, emailed me. On our group chat. So, guys, the answers were initially not posted correctly. Let me show you a trick. And this is, I guess I thought I showed this to you. Maybe I didn't. So, guys, for websites, and you guys know I code by hand, right? You guys know that? I write all my own HTML. And so for websites that are designed simply like mine, like a calendar, guys, I don't know if you've tried to parse this out, but like, for example, this was the K-factors assignment, and when you click on it, if you draw your attention up here, this is how this is set up. So obviously we're ohschemistry.org. This is AP Chemistry. Then it's Unit 6. And then in Unit 6, this is assignment number 4. And then these are the OH for overheads. So those are the slides, which are right now very, very slow to load. So then if you go to here, you'll notice the link, again slow to load, are 06, 04, and then SOL for solutions. So, for example, so what I did is I actually created the link wrong, and this said 03. So initially, when you went out to get the K-factor solutions, I don't know why this is so slow, you guys. Let's not do this way. This is ridiculous. Here, we'll just pull it off of my hard drive. So guys, starting the conversation over, when you go out to my website then, when you originally pulled up the solutions for the K-factors assignment, it was this that was wrong, because this is assignment number 3. If you had just changed this to a 4, it would have brought you to the next assignment. And guys, a lot of websites, especially websites that are simply delivering information like this, are set up like this. So if you ever get stuck in a spot like that on any website and you're like, wait a minute, if you can figure out the organizational structure, you can then get access to stuff that maybe aren't even directly linked. So there you go. Oh yeah. All right, so with all of that said, let's talk factors that influence the value of K. What do you need to talk about? Yep. Go ahead, Maddie. 82? Wow. Yes.
It was talking about particle signs applying to certain capitals.
Okay.
I understood the bit where if it's small enough
Yeah, there's so much interesting stuff in that simple question. Let me repeat it back just so everybody heard it. So how is it that we get increased surface area with smaller particles? Functionally, right? So I can draw you pictures, sort of, but there's lots of interesting ways to talk about this. But then there's also lots of interesting ideas even contained within the answer. So imagine that we have a circle. We'll say it's a circle, it's really a sphere. All things are three-dimensional. But the idea is that the surface area of this, let's say it's two-dimensional, the surface of area of this is simply the circumference of the circle, right? Okay. But then what can happen is, let's just do this grossly, if you will, but still, here, let's do this. Let's just cut it in half. And you understand that if you take something that's circular, like a cell, this is kind of where this is going. If you take a cell and cut it in half, it's going to form two new circles, right? These things tend to collapse to spheres. But the idea is that if we were now to figure out the surface area of this, it's no longer just the circumference, it's the circumference plus the diameter. And so every time you do that, you're creating greater and greater and greater amounts of surface area because you're taking something and you're exposing portions of it that weren't initially surface. They would functionally have the same volume, well, in this case, the same area. We're thinking two-dimensional, but they would have greater surface area in total, and that's sort of where this is headed. And frankly, the biology implications of this are crazy. First of all, why? Exactly. And why are cells spherical rather than like rectangular? And the idea is that it maximizes surface area while minimizing volume. There's all sorts of crazies. Spheres are really cool. But anyway, that's the idea. And a great application of this is why is it when you're starting a fire, why do you make kindling? Right? I mean, if you take a log and you chop it up into kindling, why is it easier to light kindling than it is to light a log? And the answer is because an increase in surface area. Every time you split the log, you're creating more surface area. And when you get down to the order of kindling, now you've got so much surface area that you can light it with a match. So, is that okay? Okay. Anything else there? Kate, you had a question. 13? Lucky number 13. And guys, while we're doing this, could I ask you to I know that sometimes you're thinking you have a question and then you're like, maybe I'm not going to ask it. Guys, if it's questions about catalysts, please do, because we did a really wiki quick we shot through catalysts. So especially if you have catalyst questions, even if they seem insignificant, please ask. Did you say 13? What in particular? Anything or just talk about it? Okay, let's go back and look. And guys, again, you're going to need your books today, whether you need them now, so you may as well open them. I know, crazy idea. Oh, hey, there's a catalytic converter. Oh, 592. That's what all those meth addicts stole off the buses up in Canyons District. So 13. Okay, so it says, based on the following reaction profile. So when I see following, that takes my eye to the upper right-hand corner, Cade. Because these go in, what? Oh, 4? I thought you said 13. What number are we doing? 13. It's in the upper right-hand corner. So it says, based on the following reaction profile, but follow the number. So it goes 11, 12, 13, then 14's in the right-hand column. It's not below, it's on the right. So these are broken into sections by subunits in the chapter, but 13 wraps around from the left-hand column to the top of the right-hand column. So that's the diagram they're actually asking you to look at. Do we still want to talk about it? Yeah, let's keep going. So it says, based on the following reaction profile, how many intermediates are formed in the reaction of A to C? So let's talk. So an intermediate is the configuration of molecules or whatever that exists at the peak of our reaction diagram. Wow. That's a fast reaction. It's more like a ski jump. But the idea is that whatever's up there is what is called an intermediate, or some people call them activated states or activated complexes. So again, we've got reactants over here, we've got products over here. I'm not right-handed. But the idea is that when the reactants collide, there's this moment where they're sort of stuck together but sort of not stuck together. And if they have enough energy to remain stuck together, the reaction will go to products. If it doesn't have enough energy to stay stuck together, they fall back apart and they go back to reactants. That form or that structure at the very top of the peak is an intermediate. So everywhere you have an activation energy hump, you will have an intermediate. And so that would be 2 because we have 2 humps in that diagram. I'm guessing the next question is going to be, are there any are there any intermediates? Based on the following, how many I used the word intermediate. I meant transition state. So how many transition states are there? Are you okay with the idea of 2? Okay, now which step is the fastest? The first or the second? So let's talk. This is important stuff. So it goes like this, and then it goes up and down, and then up and then down, and then down. Okay, so guys, we understand that this would be, do they call it activated complex? I want to use their word, transition states. So this would be a transition state, this would be a transition state. Then let's call this 1 and let's call this 2. And so the next question then says, hey, oh, thank you. Oh, guys, those are your AP books. Huh? Oh, we're so happy. So guys, which step is fastest, 1 or 2? 2, why? Hump is lower, slower activation energy, easier to get over the hump. 3, is this reaction exo or endothermic? How do you know it's exo? Products are below reactants. Is that okay? All right, then does it, oh, go ahead. No, not at all. No, but what we could say is this. The one that's highest is the rate determining step. But no, not at all. The first one does not have to be the highest. It could do low and then high. Yeah, and that's really not chemistry we get into a lot, but no, it doesn't. It's not always that way at all. Okay, so guys, reading on, I think the question is, oh, are we done? Oh, they never even ask us about, is there an intermediate? Never mind, we're done. Okay. So, guys, what else? But it says how many? Oh, shoot. Okay, so guys, we got to be really careful because I may have been mixing words and we need to start over. So the first question said, how many intermediates are formed? The answer to that is not 2. It's just 1, and they call it B, I believe. So guys, that trough is the intermediate that is created by the first step and consumed by the second. So there's 1 intermediate. Then, Kate, I think I may have used my words sloppily. The second question was, how many transition states are there? That's 2. Is that okay? And transition state, oh, I labeled them properly. Those are the states that exist at the tops of the activation energy curves. Those are transition states. Intermediates are the things that are created and then consumed. We okay now? Okay, what else do we need to talk about? Josh, you had an idea.
You just talked about 15A.
Yeah. 15? Huh. There we go. Oh. Yeah, let me get this out of the way and then let's talk. All right. Oh, shoot. Okay. So it says, let me catch myself up on the question. The following diagram represents an imaginary two-step mechanism. Let the red spheres be A, greens B, blues C. Write the equation for the net reaction that is occurring. So net is the overall reaction, right? Okay, so, shoot, I need a decoder. So A is red, B is green, and then C is blue. Okay, so looking at our reactants, the stuff on the left, I've got the two reds, which is A2. I've got a blue-red, so that would be AC. Then I've got another blue-red, so that's two ACs. Then I've got two red-reds, so that's two A2s. And then I've got a red-green, which would be AB, but I've got two of those as well. Okay, so simplifying that, it would be A2 plus AC plus AB. Is that okay? Well, but it looks to me, and I'm doing this live without a net, it looks to me like you've got two of each one of these. So in my mind, I'm thinking it would simplify to one of each of these. But I guess there's the possibility that that wouldn't work. No, we continue with two of each in each step. Yeah, I see, and that's why I got rid of the twos, because there's two of them in each step. You've got two of each in each box, so I just simplified it to one. Is that okay? Okay, just 1 second. And then that takes us to the middle box, which would then be, are you okay with decoding that? The colors equal letters.
Yeah, so the middle box is like the intermediate kind of things, like the first box is reactants, the third box is products, and that is the step.
So let's do this. So this is the box on the left. This is the box on the right. And these are the same. You use the word intermediate, which is an okay way to think about it. So this is box left. These are box middle. This is box right. And then adding them all up, what doesn't cancel is this. Is that okay? And again, I know that might have been confusing about the twos, but I just simplified them all because there's two of each in each box. Is that okay? Okay, go ahead. Just a second. Oh, good question. Yeah, no, and I'm glad you're... So A2 literally means an A bonded to an A. Okay? 2A means two individual A's that are not bonded together. So think about it this way. This tells us what it is. This tells us how many of them there are. Is that okay? Okay. Are we good? Maddie, go ahead. I have no idea. What's the catalyst? A2? Oh, why is that how do they lead us to that? Oh, and that is... Got it. Yeah, so it wouldn't be wrong to do that, but I don't know that there's anything in the question that would have led me to it. But yeah, technically you could put the catalyst above the line. Yeah, and that would make it heterogeneous. Not necessarily. Could be hetero or homo, but yeah, either way. Are you okay? Kaylee, go ahead. Right. So, and that's what I was trying to, I think, communicate to Maddie, although I didn't do it well. Typically, I've never seen an example, especially when we're doing reaction rate chemistry, where they say where there would be a catalyst that gets represented in that overall reaction. I wouldn't worry about it. What else, y'all? Yeah. Just a second. Oh, okay. Oh, shoot. What question number? Oh, 88.
Yeah.
Okay, hold on. Thank you. Okay. Yeah. I have no idea. Let's look and see. This is part of 88. So it says, why is the rate of flow of exhaust over a catalytic converter important? So, I mean, not obviously, if the gas is going too fast, the chances of it interacting with the surface of the catalyst is decreased, right? It just shoots through unchanged. I mean, if it's going too slow, I guess there's the possibility that it could clog back up in there. What did I answer that? If it's too fast, some particles may pass through without being absorbed. If it's too low, it could potentially, it just clogs and makes it gooky. Yeah, I mean, frankly, it's not anything you'd ever see in this class. It's just interesting, but yeah. So, what else, y'all? Good? Oh, yep. Yeah, just a second. You guys okay? We good? All right. So, don't let me forget. Pause. Boom. Hey, so guys, let's calendar together for just a hot second here. What's up? Oh, shoot. Thank you. I would have figured that out. So guys, remember that we are moving forward towards me heading to Mexico for a week. And so the timing actually worked out very, very well. But the timing is actually not this. We have 3 more days of material in this unit. They're all in chapter 15. We're moving into chapter 15 today. And so when I initially laid out the calendar, we've got equilibrium concepts, equilibrium calculations, and then Le Chatelier's principle. Then I wanted to have a conversation with you about how we were going to handle Friday and then the days while I'm gone. Because then I remembered that for the last couple years, I've actually taken this day about equilibrium concepts and broken it in 2. And that is proven to be the better choice. And so that's what we're going to do. So we are not in a hurry today. We would have been otherwise. We are going to start a 2-day conversation today about equilibrium concepts. Then that'll take us also to Monday. Then on Wednesday, we will do the math of equilibrium. Then we will do Le Chatelier's principle on Friday. That then, guys, leads us into the week that I'm gone. And this is the conversation that I wanted to have with you. So, guys, we've got 2 days of things to do. And 2 days to do it. I just want to know which one you'd rather do first. So guys, in this week, we need to do the following things. We need to take the test over the unit that we're currently involved in. We need to rewrite the test from the unit that we did previously. And then we also need to do a couple chapter summaries, but that can sort of float. So guys, during class, which would you rather do first? Would you rather take the test first or rewrite the previous test first? Take it first? Yeah, and that was my thinking too. Is there anybody that feels strongly about taking the test second? Okay, so guys, that's what we're going to do. On Tuesday, we will take the current test. On Thursday, you will then have the entire class period to rewrite the previous test, and then should you get done with that, we will have chapter 16 and we'll have chapter 16 summary due. We'll wait on 17. I'll post all this on the website, but that's going to be how we're going to proceed. Yodels? Yodels. And we do not have school on that Friday. No, there's a reason, because, never mind, I was going to say something snarky. it's our no, and actually this is the case. It's our school board's effort to try to bless or take care of teachers in the midst of these crazy days. The problem is that their solutions to what they perceive to be our problems actually just create more problems. I would much rather be in school that day than try to figure out what to do now that we've got 2 A days back to back. And it's sort of a, or yeah, well, no, 2 A days. No, I understand that. And in the minds of somebody at the school board, that was probably their justification because they don't understand what it means to be a teacher. Because that does me no good, right? Because I can't let my classes get out of sync for 3 weeks and then magically snap them back into order later. It doesn't work that way. So we've actually drawn this graph. There's actually a direct relationship between teacher effectiveness and frustration based upon the changes that our school district is making with schools.
I think there would be a negative.
No. So the more effective you are as a teacher, the more frustrated you get with the changes they're making. And I'm not bad-mouthing anybody, but there are some teachers that frankly, they don't know what they're doing tomorrow. They don't plan, and so as a result, throw at me what you will. I don't have a plan anyway. Ready, set, go. But for those of us that are actually invested in doing things, and I know some classes, they're project-based, and that's fine. But for solid academic courses where you're trying to lay out a plan and anyway. So social and emotional well-being is a big thing in the district. And guys, right now I need a hug. Bring it in. No, I'm just kidding. All right. No, because actually I would go to jail. And although sometimes jail sounds better. All right. What am I talking about? Luckily, this is all recorded. So I may go to jail. Come on. There we go. All right. So, guys, chemical equilibrium, shall we? We shall. I suppose. So, guys, if you would open your books with me to page 610. And then if you would please, not bubbles, looking at the picture on page 610, ask yourself this metaphysical question: what on stinking earth does that picture have to do with the content in the unit? Talk amongst yourselves while I get ready for what we're doing today. All right, guys, join me. So here's the answer to the question. Traffic is flowing in both directions, and in either direction they have to get over the hump, which is the bridge, which is activation energy. At that point, it makes absolutely no sense at all, because in order for this to actually make sense, it would have to be the same cars going around in circles. But maybe, we don't know that they're not. All right, so guys, here we go. Quick question for you. Food coloring in water. Why does it spread out? No. Why does it spread out? Is it spontaneously spreading out? Therefore, what must be happening to Gibbs free energy? Oh, we're starting, I know. We're starting to review, you all. All right, so guys, in all seriousness, we're gonna increasingly review over time because these are things you've got to bring back. And I understand that entire unit over thermochemistry was tricky like 3 months ago. Imagine what it's going to look like when you sit down to those same questions in May, given that it will then have been 8 months ago. So let's talk. So guys, question number 1, is this spontaneous? Yes, because it's spontaneous, what do we know with certainty is happening to Gibbs free energy? It is going down. The change in Gibbs free energy is negative. Gibbs free energy is going down. Now guys, this is largely isothermal, right? It's not gaining or losing heat. The temperature is functionally the same. So what is the driving force behind this taking place? Change in entropy. Is entropy going up or is entropy going down? Entropy is going up. Spontaneous processes are processes in which entropy tends to go up. We understand that entropy can go down, but then there needs to be an offsetting change in enthalpy or heat. So guys, entropy is going up. Let's relate. You don't need to write any of this down. This is all review. But delta G is equal to delta H minus T delta S. So guys, what is the sign for delta S in this process? Positive or negative? Positive. So that is going up. But guys, what is T? Temperature. What units? Kelvin. What can Kelvin temperatures never be? Negative. So this will always be positive. So if we have a positive and a positive, that makes that positive, but we're subtracting it, so it's negative. And the result of this entire term then is a negative delta G, explaining mathematically what we see in our own, like up here in the beaker, that this is in fact spontaneous. Guys, throughout the remainder of the year, we're going to sprinkle in these little nuggets, not because they pertain to the current unit, but simply because they're things that we need to bring back to our memories. You guys good? Okay. Here, however, is what we're going to do with this. Guys, do you remember this from last year? All right. We are going to do the equilibrium tube game. Now guys, here's the thing that's cool about the equilibrium tube game. We understand there's a principle in science that says models are valuable because they help us understand complex things in more simple and therefore more visual ways. But guys, what we find is that there's always limitations to models. For example, the model here in the book, right? Yeah, this could be flow in both directions. The bridge could be the activation energy hump. Maybe it helps us visualize things, but there are limits to the model. Well, guys, there are limits to this model too. But the thing that's cool is that some of the limits that you don't even know we ran into last year are going to fall away this year. This demonstration actually gets better and not worse as we dig into it more deeply. So, guys, with that said, let's set the stage and then let's have conversations about this demonstration that we couldn't have even touched last time. So, guys, join me and let's talk a little bit about where we're starting. You're going to want to write some of this down, and then we're going to spend an amazing amount of time playing with this because it just gets better as we dig deeper. So, guys, what are we getting into? Well, the answer is we're getting into chemical equilibrium, so we should at least at some level define this. Because in the simple definition for chemical equilibrium, if you're paying attention, is the bridge, the opening, the conduit that allows us to dig more deeply into this. So guys, let's just talk and see what you remember. When a reaction is at equilibrium, what is equal? The rate of the forward and reverse, backward, we call it reverse. Guys, at equilibrium, the forward and reverse rates are equal. So this occurs when opposing or reversible reactions occur at equal rates. And guys, understand, it's at this point that this blows wide open. If you're writing down this sentence verbatim, please underline the word that allows us to have conversations this year that we couldn't have last year. Because what's that word? Rate. We've done chapter 14. Guys, when you think about reaction rates, your mind should be flooded with this wealth of understanding that you didn't have last year. Man, when you think about reaction rates, you're thinking about collision model. You're thinking about temperature, surface area, concentration, and catalyst. You're thinking about reactions slowing down over time because concentration of reactants goes down over time. You're thinking about all the things that you know that speed up and slow down reactions. You're thinking about rate laws. Guys, there's so much that you understand about reaction rate that you didn't understand when we did this last year, and we can bring all of that information to bear on this idea of reactions going in both directions at the same rate. And guys, that's what we're going to do. So if you need, I don't think you need to write this down, but let's make sure we're clear. The idea then, again getting into rate, is when a reaction is at equilibrium, the reactants are forming products at the same speed or rate that the products are turning back into reactants. Are we all in agreement with that? Okay, then here's what you're going to do. Skip down 3 lines in your notes, if you would, please, and write this down. Make it big. Because I'm headed for Mexico in a couple weeks, could we say grande? Can I tell you guys? I took 4 years of Spanish in high school, sadly from a woman that was an alcoholic. She came to school hungover a lot. So we took a lot of siestas and had a lot of fiestas, but I didn't learn a lot of Spanish. So where does somebody go when they want to learn a language? Duolingo. That bird is seriously threatening. Like, I skipped a day over that 5-day break. That bird got angry. Like, it's texting me, it's emailing. Like, I seriously think it's like stalking me. So if you get into Duolingo, be careful. That bird will get you. Oh yeah, it's terrifying. I said this to my daughter, and my daughter's like, have you seen all the Duolingo memes? Have you guys seen those? It's for real. Okay, so guys, this then is where we're at. We are going to talk, again, using our blue tubes, we are going to talk about a simple process in which reactants turn into products, and products then turn back into reactants. Do, though, however, guys, when you write your yields arrow, your equilibrium arrow, please write it where the top one is right pointing and the bottom one is left pointing. And then here's what I want you to do. Write the rate laws for this process. Above the line, please write the rate law for the forward process, assuming that this is elementary. Below the line, please write the rate law for the reverse process, again, assuming that it's elementary. Y'all good? So guys, typically at this point I would then say share what you did with your neighbor, but frankly my fear is that it's just going to propagate things that we need to correct anyway. And when I say correct, and correct's not the word, enhance. There are ways that we represent these things. So make yours more better. Here's how this goes. So guys, when we write rate laws, we've got rate is equal to, but what we're going to do is we are going to say rate sub F. That is going to be the rate of our forward reaction. Then guys, rate of forward reaction is equal to K, but we are going to say K sub F. K forward. But then guys, all rate laws include concentrations, and so when we're talking about the forward reaction, it's the concentration of what? The reactant. So we're just going to go brackets, reactants, and boom. Now guys, based on that, please clean up your rate law that you wrote beneath for your reverse reaction. One is forward sub F, the other is reverse R. Clean it up or enhance it as the case may be. You guys okay? Okay, so then I think so we've got rate is equal to rate reverse is equal to K sub R. And then, guys, what goes in the brackets? Products. Because the products become the reactants in the reverse reaction. Okay. Anything there we need to clarify or talk about? Y'all good? All right. So, guys, for those of you that either haven't seen or don't remember how this demonstration goes, guys, we're going to spend some time with this, but let me do this for you just quickly, and then we're going to slow down and we're going to talk. But I think some of you either don't know what we're doing, or you just don't remember, you haven't seen this. So, guys, the blue food coloring water represents everything, the matter, the system. Ooh. Reviewing for the AP test. If this is the system, what does that make everything else? The surroundings. Okay, so guys, again, the blue food coloring water represents all of the matter in the reaction. And so when that blue food coloring water is in this left-hand tube, you'll notice it says reactants R, and then when it's over here, it represents products. Then, guys, what we do is we use these glass tubes to move stuff from reactants to products and then products to reactants. And so the way this demonstration goes is we place these in here, and you may not remember that the tube that we're going to use to move things forward is physically, can you see it's larger in diameter? Is that so? Literally, I think one fits inside the other. Oh, not anymore because I rounded the edges. But can you see that this one's bigger? I guess it would go like this. This one's bigger. Okay. So, and then guys, what we do is we use these tubes then to transfer the liquid moving forward. But then, of course, initially we have none to move back. And then as we continue, we're moving things forward and we're moving things backwards like so. And then we just keep going. So is that enough of a refresher to remind you? Okay. So guys, these then are the questions that I'd like you to answer. I'd like you to skip down 3 lines in your notes, and please do this. So just to be clear on terms, these are the tubes and these are the cylinders. Okay. So here's the question. Just write down the word cylinder equals tube equals cylinder, did I say cylinder? Cylinder tube, rate equals, and that'll be a good start. So guys, the question is this, and maybe we should be more clear. When you said tube, make it diameter of tube. So here then are the questions that you're going to answer. In this demonstration, and you know what, we should clarify this too. Volume of, can you say with cylinder, it would be the volume of the water in the cylinder? That would be better. Let's make that. I was trying to make this simple, but I'm realizing if I don't give you enough detail, you won't get there. So guys, where you wrote down the word cylinder, make it volume of water in the cylinder. Just volume water in cylinder. And then where you wrote down tube, again, you need a little more clarity. Diameter of tube. And then rate stands on its own. So here's then the question. What in this demonstration, or where in this demonstration, let's say this, what's the connection? Because what is the connection between the demonstration and the stuff that you wrote on the board? Make the connections. You got 30 seconds. What are the connections?
Can you send down Brucia Henry to the office?
Is it critical?
Can she, whenever she can come.
Okay, I'll send her down at the end of class. We're in the middle of something meaningful.
Okay.
Thank you.
Thank you.
Unless, Prisha, you know you need to go, I mean, that's up to you. My guess, student of the day. Which means we split the candy bar. As a class. So guys, let's talk about this. This is where this starts to get interesting, because as you're reflecting upon the connections between what's on the table and what's on the screen, guys, there are some really interesting things going on here. So without doing this in order relative to the way I laid these out for you, let's talk. So guys, first of all, let's talk about the volume of the water in the cylinders. We understand the water is just material, it's matter, it's stuff. But guys, when we start a reaction, you'll notice we've got a lot of water, 100 milliliters. The volume's 100 milliliters. We've got a lot of water in the reaction cylinder, and we ain't got no water in the product cylinder. Guys, where do these water volumes tie in? Where are they represented in what you wrote on the screen? They are the concentrations. So guys, if you don't understand this, you may want to jot note to yourself. Volume is analogous with concentration. So guys, let's put this in the terms then of the demonstration. And keep track of the numbers. This is 100. This is 100 molar. Milliliters are analogous with molarity. So guys, this is a lot. But when a reaction starts, by definition, how much product do we have? None, right? So guys, do you see the relationship between concentration and volume? Is that okay? Okay. So then guys, question number 2 is this. What do the diameters of the tubes represent? This is tricky. This one's hard. What do the diameters of the tubes represent? They are the K values. Guys, the diameters of the tubes represent the K values. And this is where this gets really interesting, and we're going to answer the last question. But guys, let's do this first. So the bigger tube is the forward reaction, the smaller tube is the reverse reaction, and as a result, guys, K forward, if you want to jot a little note to yourself, this is large, and this one is small, Oh, shoot. Oh, gosh, thank you. That was just wrong. Thanks for catching that, guys. This is K sub R. Sorry. Wow. Did you guys just think K sub R and not catch that? Okay, because, guys, the K values are not the same. The forward and let's talk about why. Guys, the forward and reverse K values are not the same. Why not? Because the activation energies aren't the same. So guys, the forward K values, the forward activation energy and the reverse activation energy, here's your forward, here's your reverse, because these are very, very seldom, if ever, the same. Just saying. Okay, so let's get rid of that. Oh, and we made that into reverse. Okay, are we good there? Now guys, this is where this gets really interesting. Where in this demonstration is rate represented? This one's really tricky. So guys, watch. When the reaction starts, we have a bunch of reactant to turn into product. Big rate. But when the reaction starts, we don't have any product to turn back into reactant. So guys, what is the reverse rate when this reaction starts? 0. What now in this demonstration represents rate? Where is there a 0 represented moving backwards? Exactly. The amount of water in the tubes. And guys, this is where this gets really interesting. And you probably haven't thought about it this way, so let's talk. And don't write this down, but you understand that these are technically multiplied together, right? K times concentration, K times concentration. Guys, the multiplication is happening in the tubes. Guys, check this out. This is going to make a mess. Guys, we have a large concentration of reactant, right? We have a large K-value tube. And so when we take a large K-value tube and we multiply that by a lot of reactant, guys, we got a pant load of water moving in the forward direction. And it's this amount of water that represents the forward rate. Does that make sense? Now, guys, check this out. Moving in the other direction, we have a smaller K value, but how much product do we have? 0. And any number times 0 is 0. We don't have a reverse rate because we ain't got any product. Do you get the idea? But now, guys, watch this, because this even gets better. Ready? Let's pretend for a moment that this reaction is not reversible. Let's just focus on the forward reaction. So when the reaction starts, huge K value, huge amount of reactant, a bunch of reactant that turns into product. Do you see that this is representative of rate? Now, guys, let me ask you this. Relative to the first time I did this, how much water is in here now, more or less? Less. What is this amount of water representative of? Rate. So what is happening to the rate of the reaction as the reaction goes on? Why is it slowing down? The amount of react. Do you see how this is a visual representation of something you learned weeks ago? That reactions slow down because we have less reactant to turn into product. So the reaction is consuming itself. So every time we move reactant forward, there's less reactant to be involved. So the amount of reactant moving forward is less and the reaction is slowing down. Do you get it? Yeah, right? Isn't that interesting? But guys, this is then the interesting bit. Let's bring in the reverse reaction. Products. What is the reverse rate initially? 0, because there isn't any product. But now, guys, watch. When we do this first step, the amount of reactant turning into product is huge. But we don't have any product to turn into reactant. But now we do. So what is now the case for the amount of water, the rate in this tube? Smaller, less is slowing down, but what about the other tube? It's bigger, and so the forward rate is slowing down, and the reverse rate is speeding up. And when this thing finally reaches equilibrium, what is equal? The rates. And where is rate represented in this? The amount of water in the tubes, and we are eventually going to get to the point where the amount of water that we're moving forwards and backwards is the same, and at that point the rates are the same, and that is when we reach equilibrium. Does that make sense? All right, now guys, let's get there. Do any of you happen to remember the ratio? 70-30? That's kind of what I thought as well. But again, it's been a while. It's kind of hypnotic. You are getting sleepy. Some of you are going, I already was sleepy. Now I'm sleepier. I think we're probably there. Let's look. Oh my gosh, you remembered it's 70-30. All right, that's weird. Yeah, it is actually 70-30. So guys, now that this has reached that point of equilibrium where we're at 70-30, if I keep doing this, what's going to happen to the amount of water in the tubes? It's going to stay the same. What's that? Minus the dribbles, right? Those are side reactions and impurities. So guys, now let's talk about what's going on at equilibrium. So guys, at equilibrium, what is equal? Don't miss this. At equilibrium, what's equal? The rates. That is represented by the amount of water in the tubes. But you'll notice, guys, that at equilibrium, the volumes in the cylinders are not the same. What is that representative of? Concentrations. So guys, at equilibrium, the rates are equal. I see some of you writing this down, not a bad idea. At equilibrium, the rates are equal. But guys, at equilibrium, what is true of the concentrations? They're not equal, they're constant. They are unchanging. You guys sold on that? At equilibrium, rates are equal. At equilibrium, concentrations are constant. Good? Now, guys, check this out, because we're going to go back to the board, and this gets better. So here's our forward reaction, and we're going to talk about bigger and smaller. So, guys, for the forward reaction, what is true of the concentration of our reactants? Compared to that, is it big or small? Small. But, guys, what's true of our K value? Big. So a small concentration times a big K value, and then here we have a small K value and a big concentration. And guys, this is how those end up equal. So we have a small concentration times a big K value, and we have a small K value times a bigger concentration, and that math ends up equal. Do you see that? Let me roll for a second. Does that make sense? Now, guys, this. What is it that determines this 7-to-3 ratio? The diameters of the tubes, which is representative of what? K values. Guys, at that point, please write this down with me. Back in general chemistry, guys, we learned to write what are called Kc values. Do this with me. This is not little k. This is big K. And Kc values are defined as product divided by reactant ratios at equilibrium. Product on top, reactant on the bottom. Is that okay? Now, guys, what I want to do is I want to bring you back to Chase's important thought, and then we're going to do some mathematical gymnastics. You ready? Think through this with me. So, guys, this came out to be 7-3, right? Why 7-3? Because the ratios of these diameters, which represents little k, they're not the same. If these had been the same tubes, they'd end up at 50-50. But guys, they're not the same. So there's a relationship between this ratio and that ratio. You okay with the idea? So what is the relationship? And guys, check this out. So here's the idea. We are now going to talk about this system at equilibrium. So if it's at equilibrium, what is true of the forward rate and the reverse rate? They're equal, yes? So guys, I'm going to just bang on that. So at equilibrium, these are equal. So we could say rate forward is equal to rate reverse. Good? Now let's do this. Let's substitute. If these are equal at equilibrium, do you understand that those are also equal at equilibrium? Is that you're just substituting? So if our rates are equal, and if this is equal to this, and if this is equal to this, then these have got to be equal. Does that make sense? Let's make them equal. Guys, write this down with me. K forward times R is equal to K reverse times P. Some of you are going, oh wait, I see where this is going. Do you see where this is going? It's going to here. Guys, what we're going to do now is we are going to take this relationship and we are going to solve it for P divided by R. So to do that, we are going to divide both sides by, what did I just do? Sorry, scratch that. It's an R. I was one step ahead of myself. So to do this, guys, we're going to divide both sides by R. And this is now gone. But now we need to get this by itself. So we're going to divide by K sub R. And now we have this statement. K forward divided by K reverse is equal to concentration of products divided by concentration of reactants. Now guys, let's pull this idea together by looking at our demonstration. So here we go. Our K forward is the bigger tube, yes? Our K reverse is our smaller tube, yes? Then let's add this then. So our forward divided by reverse ratio, is that going to be a fraction bigger or smaller than 1? Bigger, right? Because this is bigger than, so forward is bigger than reverse. So this number is bigger, so that's a fraction greater than 1. It's 70 divided by 30. But guys, that is also then this ratio, product divided by reactant, which is also bigger than 1. So the idea is this. If our forward K value is greater than our reverse, then at equilibrium, we'd expect to have more product than reactant. You see how that all ties together? And guys, all of this is then equal to Kc. And Kc was a big idea that we talked about last year in class. And we're going to talk about it more in the coming weeks. See how that just gets bigger and better as we dig deeper? But guys, do this with me then. Grab your books. Literally, grab your books and open to page 613. Starting at the top of page 613, look at equation 15.1. Guys, it doesn't matter what these chemicals are, but on the left we have a reactant that's colorless, and on the right we have a product that's brown. We're just going to call it clear and brown, okay? Then, guys, jumping down to equation 2 and 3, they have written the rate laws for the forward and reverse reactions. Just like we did, only we wrote them above and below the lines, but they wrote the rate laws for the forward and reverse reactions. Then they set them equal in 15.4. Why did they set them equal in 15.4? What has to be true of the process? It's at equilibrium. So at equilibrium, the rates are equal, and therefore the other side of the rate law is equal. And then, guys, they just solved for products divided by reactants, which is equal to K forward divided by K reversed, which is equal to a constant, which we call K sub C. Now, guys, here's the trick. When you read this on 613, when you were doing your chapter summary, my guess is none of that made sense to you and you skipped over it, if we're being honest. But, guys, here's the thing. Based upon some food coloring water and a couple cylinders, now all of a sudden you understand all that rich chemistry. That's the magic of teaching rather than reading stuff out of books. But it's also the challenge of learning things in college. Because many times your professors will just ask you to read rather than them teaching, and you still have to connect with the material. So guys, when you get to this point in college and you're like, oh crap, I'm supposed to learn this from a book, guys, come back to this, because it's an amazing, when you get into equilibrium further in your studies, guys, this demonstration is so rich with connections that if you can come back to this, then all of a sudden when you see something like this in a textbook, you have a much better chance of understanding it. But again, looking at equation 15.5, guys, do you understand that equation 15.5 is this? We understand that the K ratios is then represented also in the product reactant ratios, which is then represented by what we call Kc. Is that okay? Okay. Maddie, you had a question or at least a thought a long time ago. Oh, yeah. And actually, so the easier way to do that would just be by differences. You mean at equilibrium or as it goes? And I've actually done that with classes where I've actually started like this and we've collected data. So like half the class keeps track of this and the other half keeps track of this. But what would the graph look like? And interestingly, the graph looks like that, right? Because because you're tracking concentration. And so the rate at which this goes up slows down, the rate at this goes down slows down, all of that stuff is all represented in it. It's just a real huge time ask to do that. So yeah, but that's what would happen. So guys, that's our day. We got through one slide, right? So maximizing our time, whatever that means. Let's just write this down now. Here's your homework. And what I'm going to ask you to do is do what of this you can, which frankly will be very little. If you're thinking about then going, well, wait, I've got a bunch of time now, what could I do with it? You could be thinking about summarizing chapters 16 and 17 with the understanding that those will not be due until the beginning of February, unless you're Cade and he's already summarized chapter 16. And but that's fine. So guys, we're going to break there. Let me stop recording.